How you guys doing? All right, all right. I'm doing a little better myself. Thanks for asking. Um, yeah, I apologize for that last lecture. I was really hanging on to threads of consciousness myself. I'll try to do a better job today. Should be exciting though, despite the small audience size today. We're going to do two really interesting things. We're going to talk about the formation of the Earth and the interesting debates that have happened in the last century about that, which I'm really excited about. And then we're going to talk about magnets and magnetism and the Earth's magnetic situation, which is really fascinating and I think really poorly understood, and I hope I can shine some light on that. I hope you guys at least have a better idea how magnets work by the end of today. That would be a victory. Because, well, most scientists probably don't know how magnets work. So we'll try to do that. But as always, you guys know how this show goes. Let's hear from you guys about thoughts from last week, other than the fact that it was a very unenergized lecture, and I'm sorry about that. I'm doing my best. At least I made it. I need to get through some more people on this list, so I'm going to call on people who probably aren't here, and then we'll just see what you guys have to think.
I thought it was interesting that you were talking about like the Oort cloud and how there could be another planet or like celestial bodies beyond that, and then like a bigger planet, further explaining the orbits of the other planets.
Yeah, there's people working on that pretty seriously right now. There's a group at where is it, at Caltech. A guy named Konstantin Batygin who's always rolling out new ideas about where that thing might be. But yeah, there are some weird unexplained orbital patterns in the planet still that we're trying to get to the bottom of. So that's interesting. I mean, these, by the way, guys, these are like, the way that these patterns have changed is maybe something you might consider for your final project. Again, I want you guys to find a place either in the history of astronomy that we talked about or what's happening right now even. The history could be last week as far as I care. Where things are on the move, something is changing, some paradigm is undergoing revision. So pay attention to all those little pieces. The story of the planet 10, planet 9, all of that is a cool little excerpt, little example. How about Amy? Are you here? They're not quite brown dwarfs, but they're on that program perhaps. Yep.
That just clicked in my head, I guess before. They are similar. So are they different?
Yeah, and those what's up with those orbiting Jupiters out in the Orion Nebula? There's another topic somebody could pick to do for their final project. That's an interesting paradigm. Planets have to be born in the solar system, or do they? That's an interesting paradigm that's shifting. Make notes of these things as we go, because you guys are going to need something to dig around in. And I'm going to want you guys to go and pull some articles from the literature to substantiate your exploration a bit. But yeah, brown dwarfs, Jupiters, suns, something interesting happening there. It's not entirely clear that they're different things as much as different expressions of the same thing, perhaps, or even just different moments of the same thing. That's a really radical idea that I think will continue to gain purchase. Thoughts on that? Anybody else? All right. Yeah.
Kind of in that same part of your lecture, you talked about how a lot of these like planet. I mean, you kind of moved on into like talking about Neptune and like super Earths and how there's like the difference there is like a whole lot. And it's could just be that it's a progression of how the planet like kind of evolves over time.
Yeah, that's something to keep an eye on as we go forward too. And we're going to talk more about that, and we're going to talk about it a little bit today when we talk about the history of the Earth. But this metamorphic idea is really, really fascinating. I think that there's a big paradigm shift, at least possible in the near future regarding this. And as we start to see more details about it, I think the more compelling you'll see that Neptune to Earth transition making itself manifest. I'm trying to think how much I want to say about that right this second. But it's going to keep cropping up. It's a really interesting situation. And I think thinking about bodies in the solar system, just celestial bodies, whether it's stars or planets or whatever, starting to kind of apply like our evolutionary thinking that we've become so proud of in biology to when we start to maybe use some sort of similar lens to approach the cosmos. I think we might get a little further than we've gotten so far. And I think that it's becoming a little more tolerable of a way of looking at things than it was even when I started teaching this class a couple of years ago. So that's a really cool paradigm shift. And if you want to explore that one too, that's another situation. It's going to be harder to find the primary literature on that. I can point you to some stuff though if you want to do that topic. Any other thoughts? In the back, remind me your name again? Macy, yes.
I thought it was interesting when you talked about how like small like pieces of dirt and stuff like would stick together, but when you look at like pebbles and stuff, they would bounce off each other. So that's like how would they make a planet?
Yeah, it's really weird. There's a couple of those where I guess I'll touch briefly at the beginning of class today just to make sure that so I'm not going to really get back to the formation of the solar system as a whole until probably the last class or something. That's a whole topic you guys could do too. But there are some serious problems with this story, right? So this idea that everything just kind of condensed out of this one giant swirling ball of stuff. It's a cool idea. It makes a lot of sense in some way, right? Because remember this angular momentum thing. I keep saying that word, but like the figure skater, right? When the figure skater brings their arms in, they spin faster, right? So the idea is that as these things collapse, the whole system should start spinning. But there's weird problems with that. You mentioned one of them. The other one being, why isn't the sun spinning faster than everything else? If the figure skater model is how we're explaining the formation of this whole thing, shouldn't the sun have all the angular momentum? It turns out it doesn't. The planets do, and Jupiter has most of it. So that's pretty weird on its face. Now, I'll go over a couple ideas of how people try to explain that away. But then you bring in the pebble boulder problem, also called the meter barrier in planetary formation, and you're kind of in trouble because it's very difficult to get pebbles to stick together. It's also really difficult to get boulders to stick together, but pebbles are a huge problem because they don't have a lot of mass, and they do have a lot of momentum still because they're moving really fast, and they'll just bounce off each other. So what's going on? I have some ideas, right? The planetary evolution stuff is the coolest lead that I've seen, and I'm going to keep developing that because I think there's some real purchase in it. But of course, science is always constrained in its possibility set, and the biggest constraint we have for making a formation in the evolutionary model is the timelines associated with it. So, short of some miraculous, catastrophic changes in the orbits of the planets, which is totally possible, but short of that being evidenced, it's very difficult to make these evolutions happen in the short 4.5 billion years that we're given for this solar system to have formed. Largely constrained by the Big Bang cosmology, which is really interesting. So we'll keep talking about that as we go ahead. Any other thoughts on that stuff? Yeah, Dave.
I never knew that asteroids were really just like miles apart from each other. I thought Star Wars was scientifically accurate.
Yeah.
I also just think like the magnetic sphere we have around like many planets, but Earth specifically, I always think that idea is super cool. Like it's kind of our own defense mechanism against like solar flares, and just the fact that it's like our iron core is what's kind of making this magnetosphere.
Kind of, yeah. It's a little more complicated. I'm going to explain that today, though, so you can.
I got it all wrong.
No, you don't got it wrong, but it's a little more complicated than that. It is the iron core helps. So in a magnet, I actually built a little electromagnet for you guys. I want to show you how it works. But if you stick a iron core in the middle of an electromagnet, it stabilizes and amplifies the magnetic field. So the iron it's kind of like it'll just play along with whatever's going on and sort of amplify it. It's sort of like I don't know, people following trends on social media or something, right? It'll just go with it. And it actually makes it bigger because it's going to be resharing it and stuff like that. That's kind of what iron does. But the actual magnetism has to be generated by something moving, some sort of current system that's moving, actually.
The melted
Melted stuff.
Kind of like they think it's like kind of rotating in.
Yeah. But we'll get there. But before we make sense of that, I think we got to understand exactly how magnets work. So we'll do that. I'm going to try to really pace myself today so I don't get lost in the weeds. And I do want to make it through magnetism because that'll cue us up for understanding our search for life, which I want to get into next week, and the origins of life on our planet. And I'm going to bring in the lovely Dr. Benderberry, my wife, to talk to you guys about origins of life because she's smarter than me and she's good at that stuff. So hope you all will show up on Thursday for that one. Cool. Yeah, magnets are crazy. It's even crazier that nobody seems to know how they work, which is really bizarre. There's so many of these prosaic things. When I was going into college like you guys, I thought maybe I'd want to major in physics. My advisor, they assign you like a random advisor, you know, when you show up. Do you guys get random advisors when you show up? My advisor was like the physics chair. And this guy was just such a drag. And he just really made me feel like all the problems had been solved, you know? And I felt like, well, why am I going to spend I went into neuroscience instead as an undergraduate. So it seemed like it was a brand new science where nothing had been figured out. Anyways, the funny thing is, in physics, the most mundane things that we deal with every day, like magnets, right? And you might not think they're that common, but they're essentially how we generate all this electricity. So we'll talk about that. Magnetism, electricity, light, gravity, all these things that we're just so used to, we just don't even think about them. They're really, really poorly understood is the fact of the matter. So there's a lot of work to be done on this super basic stuff. Cool. Let's get a couple more. Joe, are you here? I know you're in the class. All right. Well, who the heck is here? You guys, any further thoughts about last week? Yes, Orlando.
The thing about Saturn's rings and what music.
Mm.
That was very interesting. I also didn't know that there was you showed the picture of like everything orbiting Earth. I didn't know what Circes would make. It's like what are those?
Oh, those are actually in the asteroid belt.
Oh, okay.
Yeah, but it's pretty weird because they look a lot like moons or something like that. And you can't actually, again, you can't explain those things. The Ceres, right? It's not big enough to have collapsed into a sphere. You can't balance the forces of gravity with what would give it a kind of a regular shape otherwise. So how the heck did that thing get there? It must have a story that goes deeper than the one in the textbook because it can't possibly have collapsed under its own gravity. So I don't know. When I look at these moons and stuff, these super cratered worlds, I can't help but thinking they're really, really old. And maybe they've had many surfaces and been resurfaced many, many times. It's very hard for me to imagine anything else. At least with something like Ceres, which clearly, if it did come together in some sort of gravitational process, it must have been much bigger at some point in time. But it doesn't seem to have like blown apart or anything. So that means it's kind of weathered down. And that must have taken a really, really long time. Which again gets at my little beef with this timeline. It just doesn't seem like enough time to have formed a lot of the bodies that we're going to be examining. So, yeah.
I also thought it was interesting about when we're talking about Mercury, how you said it was like shrinking.
Was it Mercury?
Yeah, it's one of the. It just made me think about the inverse. Because I watched your podcast about did Earth become a mini Neptune.
Yeah, we're going to talk about that today for sure. Yeah, that's a really interesting story, especially because it was such a hotly debated topic. There's something funny that happens that's a little unfortunate in science, which is like sometimes we'll have these huge battles between competing theories, but they usually are solved really quickly, or like the consensus jumps on one versus the other, and then people forget that there was even a debate in the first place. And the one that you're referring to, this it almost sounds like flat Earth when you say it out loud, but this expanding Earth idea. It was actually a strong competitor at the time. And I'll talk to you a bit about the history today after we get there. Cool. Let's do one more question, one more thought from last week. Somebody. Yeah, please.
The Greeks and Trojan for Jupiter. I had like heard of the like, I know that we have satellites for Earth that are like in the kind of same points for the orbit, and I knew about that, but I didn't realize that Jupiter had these like massive pools of asteroids.
Yeah, pretty wild. Yeah, and Saturn doesn't, which is really even more weird. Yeah, that's a sort of unexplained mystery as far as I'm concerned. The explanation that Jupiter just stole all of Saturn's never really sat with me too well, but I haven't really dug into it. So that's an interesting little topic for sure. The Trojans and the Greeks. Yeah, you know, yeah. There's so much to be said there. We'll deal with it more when we get to the asteroid belt. I think we'll spend some time on that individually. I guess I'm gonna keep rolling though, so I want to make sure that I get to magnetism today. Oh, I saw this. I wanted to show you guys this headline if I can show it real quick. This is another interesting paradigm that's on the move. It's kind of a less than consequential example, and it's not really about the solar system. But if anybody wanted to follow last few years of how this argument has changed, it's been a real roller coaster too. Betelgeuse, it's the shoulder in the Orion Nebula. It's the big. If you go out at night, it's kind of this yellow-red star right above the belt, upper right-hand shoulder. So yeah, a few years ago when I started this class, they thought it was kind of about to go nova. And then that didn't happen. They changed their mind, says it's about to go. There's some dust in between us that's periodically showing up, which is dimming it in some regular sense. And now the idea is that it's actually a binary or trinary star system. And like the whole point, look, I'm not trying to like ridicule these people for changing their minds. That is not what I'm trying to do here. I'm trying to show you guys how we're always evolving our stories about things. And it's really important that you understand that that's literally what science is supposed to do. You're supposed to sit there and stare at multiple theories and make your mind up. Not have somebody make your mind up for you, but make your mind up about which one makes the most sense to you. So if anybody wanted to touch on that one, where the heck's my mouse at? Sorry, guys. Come on. That'd be an interesting topic for you. Okay, cool. Let's just wrap up a little bit about this solar system formation thing. I want to make sure that there's nothing that I missed here. Like I said, I won't be able to get back to it for a while. We talked about some of the problems with this model. The model was created essentially by Descartes, Laplace, and Kant, the philosopher Kant, almost, 300 years ago. And this is, I think, Descartes' original drawing. It's a pretty simple idea. It's the figure skater idea that I just talked about. It's been through a bunch of revisions over the years, which is kind of interesting. So people tried on all sorts of ideas. The idea that perhaps the individual, let's say another star was coming by our star as it was forming and sort of yanked all of this goop out of the sun, and it made little planet droplets as a result of it. That was a popular idea for a while. What else? This is the one that I'm talking about here. The idea that perhaps a nearby supernova exploded and gave the little droplets that became the planets was another idea. I think in general, science in the 20th and 21st century is very allergic to catastrophism. So the idea that these black swan events could, produce serious effects. So anything regarding massive changes to this existing kind of balance that we have right now is really unpopular. There's actually good reason for that. So back in the 1800s, archaeology was becoming an actual science for the first time. And half the archaeologists looked at all of the archaeology and they said, well, this is evidence of the Bible, essentially. Like that the earth was created 6,000 years ago, blah, 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 blah. They saw signs of floods everywhere. Turns out there are signs of floods everywhere. But the other half, and let's say the more progressive arm of the scientific community, was like very allergic to bringing religion into science. And so they took the stance that, they were very much opposed to the other camp, who kind of said that everything in the past that had changed was a result of catastrophes that had happened. And you see these catastrophes throughout religious literature in general, right? So science kind of developed an immune system, I think, at that point in time against catastrophism. And perhaps that's unfortunate because it's ruled out a lot of interesting hypotheses along the way, because people really want to believe in this gradualism, that all the processes we see on Earth, they all kind of happen nice and slowly. Evolution was this nice, slow process, and everything is quite predictable and regular. So that is a comforting worldview, and it would be nice if it were true. But we've kind of inherited that hopeful, what's called uniformitarianism, that things proceed according to a nice slow plan. So a lot of these catastrophic explanations for the solar system were thrown out as a result of catastrophism just not being a popular way to go about science. There was this interesting dude named Hannes Alpha, and we're going to talk about him next semester more when it comes to the sun. He actually proposed, as far as I can tell, the most reasonable... Oh, please, yeah. It does, exactly. Exactly. So...
Just to have bigger events be possible.
Yes. Yeah, exactly. So that's why people hated it, right? Because the catastrophists were generally using it to argue for a really truncated timeline for the entire universe, let's say, but definitely for the Earth. So I think the scientific mainstream became really allergic to catastrophism in general and associated it with these kind of religious nuts. However, I do think that weird things happen. The fact that there's even life on this planet at all is pretty weird. It seems to be pretty unusual and rare. So rare things definitely do happen. It's just a matter of, can you provide an actual mechanism for it? And I think that's really the best way to evaluate theories in general. It's like everybody's going to have evidence, right? Hopefully it's not garbage and made up, but assuming it's not garbage and made up, you have to really look at the story that they're telling. Does it flow from A to B to C? Are there missing frames in the story? Those are really difficult questions to answer. But once you have that, then you can maybe compare the theories and see what makes most sense to you. So, one of the biggest problems, like I said, is this angular momentum problem with the gas ball collapse thing. And this guy actually, he proposed a solution that I think kind of rescued this model for most of the 20th century. He essentially argued, amongst other things, he was a Nobel Prize laureate regarding some of his ideas about how the magnetic features of the sun were made. So those coronal loops and things like that. The sun has a very beautiful magnetic pattern on it. He won his Nobel Prize for that, but he also proposed on the back of that fame that one of the ways that the solar system might have slowed down was through this kind of transfer of momentum from the sun spinning into that dust ring and that gaseous ring that would condense to form the planets. So he had this kind of magnetic braking idea that you would essentially charge up that system and slow down the sun as you did it and speed up the rotation of everything else. I don't know if I buy it, but it's a reasonable proposal. It's interesting. So the solar system went through they tried out all these different ideas, and nobody could really come up with a better idea, which is funny because we've essentially come back to the same idea that we had back then. Told you guys about the supernova idea. So we've essentially arrived right back where we started, which is quite interesting. And there was one thing I actually wanted to read to you guys. This is a little bit unrelated, but I think it's interesting. I'm actually reading Francis. You guys know who Francis Crick is? DNA guy. Ever heard of him? Watson and Crick gave us the nice structure of DNA that we have today, along with this lady named Rosalind Franklin. There's a huge debate about whether they just kind of stole her ideas and profited off them. Maybe. But he wrote a book about the origin of life, which is kind of interesting because he's a panspermist. He thinks that life came from somewhere else. It didn't just pop up on this earth by itself. But he gave this really interesting description, which I thought would have been a good summary for just how bizarre and like empty the solar system is as a whole. So I think it's hard, like Rolando, what David was talking about. There's a lot of space in between all of these different bodies, and I think it's really hard to comprehend. And I really liked how he described it. He said, by analogy, the size. He goes, let's think of the sun as the size of an orange. On that scale, the Earth is a grain of sand circling in an orbit about the sun at a distance of 30 feet. So think about that. An orange, and the Earth is 30 feet away and the size of a grain of sand. That's really interesting. Jupiter is 11 times larger than the Earth, so a little tiny pebble. It is revolving at a distance of 200 feet or a city block away from that orange. So that's crazy far away if you think about it that way. Now, the galaxy itself has 100 billion of these oranges in it, but each one of them is separated by a distance. Each one of these stars is on average separated by a distance of about 1,000 miles if the suns are the size of oranges. So everything is really, really far away from everything else, which makes these explanations all the more difficult because you're trying to talk about influences on such a vast distance. And gravity, of course, falls off with a really, really intense inverse square law. But it's really empty, so there's not a lot of stuff going on, and the influences do pile up. But I thought that was just a really cool visual analogy for exactly how small, or well, actually how vast the distances are between all these different planets. All right, so I think we've beat that horse pretty hard. Yeah. Just to give you guys an idea, so if, one thing that I always thought was really interesting is this idea that when the stars stars have a life and they die, and we'll get into it next semester, the eventual outcome of a star that you guys are probably most familiar with is that it explodes into something called a nova. There's another pathway for stars, which is that they just sort of die slowly, right, and create these remnants. But given the timelines that the astrophysicists have come up with for how long it would take for a star to cool down, and by the way, the remnants, what do they look like? They look like little round balls of rock. They look a lot like moons or something like that. Now, so again, why don't we think about the idea that moons or these weird-looking dead rocks are the remnants of stars? It would take about 1,000 trillion years for one of those stars to cool off to the point that it looked like a moon, is the answer. Now, of course, 1,000 trillion years, a trillion is 1,000 billion, so 1,000,000 billion years is a lot longer than our Big Bang of 14 billion years that we have right now. Like I said, there's a lot of reasons the Big Bang's on the ropes, but it's a very, very, very long time that it would take for some planet to cool off to the point that it looked anything like a planet or a moon or something like that. Now, does that mean that's not what they are? I'm not sure it does. It just means that our timelines are woefully inadequate for those kind of processes to occur. So we're talking about a really, really, really long time for a star to cool down. Now, as a star cools down, though, like if it does go through this, what's it going to look like as it cools down? Well, it's probably going to look like a brown dwarf at some point, right? Once it stops doing fusion. And then at some point after that, it's probably going to look a lot like a Jupiter. So, there are metamorphic possibilities at play. The timelines are just incredibly long for the most part. And that's troubling to standard model. Okay, let's talk about the Earth, and then I'm going to talk about the formation of the Earth, and I'm going to talk about the magnetic field of the Earth, the magnetism. And like somebody mentioned that magnetism is kind of, the magnetic field of the Earth is kind of our savior, and it really is. It seems to also be wholly unique in that such a small planet would have such a powerful magnetic field that's actually able to save us from all sorts of nasty radiation and horribly fast-moving atoms that would just crush our DNA out of existence otherwise. So what do we know about the Earth? We know it's really, really dense. It's mostly made out of heavy stuff like iron and silicon, some oxygen. Silicon oxygen is basically sand. It's also in this really bizarre place where it's just warm enough to have liquid water, but not too hot that the water boils. So it's a real just right planet. Of course, everything that we are going to talk about in this course and next course is standardized to the Earth, which is kind of interesting. So when we talk about units of pressure, for instance, we'll say atmospheric pressure on the Earth is 1 bar, which is just about 1 atmosphere. That's the other unit you'll hear it in. So when we hear the pressure on different atmospheres, they're basically normalized to Earth. And a lot of our standards of measurement are normalized to Earth. So, the semi-major axis of Earth's orbit, of course, 1 AU, right? So when we talk about distances to other planets, we consider them in AUs. So we're very geocentric about this, and I suppose that makes sense to some extent. This is the picture of Earth that was in my astronomy textbook when I was a kid. I don't know if it's the same one you guys have in yours. This looks pretty similar. It's a little bit, this just evolves quite a bit actually. So at least when I was a kid, I was told there's like this core, there's kind of a liquidy hot part over that, and then there's this rocky mantle over top of that, right? Turns out this rocky mantle thing is a lot more like a different viscosity of liquid than an actual chunk of rock. It's very liquidous under the surface. Actually, if you peeled back and took the crust off the Earth, it would look a lot like a cold star, which is an interesting thing to consider. So what's going on with that? How do people even know this stuff? Does anybody know how they figured this out? Yes.
Well, wasn't it like the weight and stuff? Without-
Yeah, exactly. Exactly. Shout out to another female physicist. This was a Danish lady named Inge Lehmann. And she was actually examining exactly that, the way that seismic waves propagated from one side of the Earth to the other. And did these really cool echo studies where she was able to show that they're, because if you make a vibration in something, the vibration typically depends on two things. It depends on the stiffness of the material and it depends on the density of the material. In either case, it doesn't really matter which one's different. There appears to be multiple layers of material inside the Earth, in particular these two parts, right? Which I think is where the outer core versus the mantle is how we got this picture of the Earth having this rocky mantle underneath. That evolved a little bit, so it's still believed that like the continental crusts, let's say, right, the places where we actually have land for the most part, those are a different kind of rock. It's a kind of rock that's basically granite. Whereas a lot of the others, rock is this kind of cooled basaltic rock underneath the seafloors and stuff. I think I mentioned to you guys the seafloors are actually really, really young, which is quite interesting. And we'll come back to that in a second. So yeah, they figured this out. They figured out there was layers to the Earth, at least. This was back in 1936. It's actually freaking crazy if you think about it. This has been less than 100 years since people came up with this basic idea that's kind of taught to elementary school kids today. That this is what the Earth looks like inside. It's like, wow. So much of this is just very recent knowledge. It just continues to blow my mind. But I think it should open our minds up as to how far we have to go probably too, which is really exciting. What do I want to say about this? So the crust covers about the continental crust that I was talking about, the granite section. It's about 6 kilometers thick. And, it's about 20 kilometers thick, and it covers about 45% of their surface. The rest, that oceanic crust, 55%, it's about 6 kilometers thick. But then, of course, down below it is just very similar, more of the same stuff at a different density. So that stuff, by the way, is basically what you see coming out of volcanoes. Pretty standard basaltic rock, cooled from a molten state. We also have sedimentary rock too. You guys have probably seen this. People have tried very hard to use sedimentary rock for dating of things because it's obviously layers of junk that just piles over top of bones and things like that. Turns out to be really tricky to use as a dating method because sometimes you get really wild weather or mudslides and stuff like that you can't just say that one layer equals so many years because the years are very, very different in terms of what happens during them. There's also, let's see, we can skip over that. There's another type of rock that mentioned in your textbook called primitive rock. These are thought to be, primitive rock is really old rock. That's basically what it is. But it's thought to be the remnants from when the Earth was formed. But of course, that's really just because it's the oldest rock that they've found more than anything else. Similar density to, this is kind of interesting. So meteors actually seem to have a similar density to a lot of these ancient rocks too, which is quite interesting. Let's see what we want to say about that. Okay, let's talk about the Earth's formation a little bit. So this is the idea that you guys probably read about in your textbook. plate tectonics is kind of at the heart of it, but the theory itself is actually called continental drift. So the alternative theory I'm going to present to you in a second is also a plate tectonic theory. The idea really just comes down to how do those plates move around? That's the real question. So plate tectonics is just the simple idea that there are fractures on the surface of the Earth, that they have changed location over time, and there's some good reason to believe that that is the case. I'll show you in just a second. The question is, and that they were actually contiguous with each other at some point in time, that these plates were actually touching one another. The question is, like I said, how did that happen? What did it look like? Was all of the landmass on one side of the planet like it is in our textbooks, or was something else going on? Why do they think this, by the way? So this is kind of the best piece of evidence, and this is really what got the party started too, was that archaeologists started digging up bones of ancient creatures that they would only find certain ones of these creatures very close to each other, but with a whole body of water in between them, right? So if you look at this graph, you're basically looking at the spread of certain species of dinosaurs and things of that ilk from millions and millions of years ago that seem to occupy similar locations if you slam the continents together so they're touching all of a sudden. Make sense? So this is, I think, completely reasonable. It's very hard to explain, for instance, how this little, or probably a really big lizardy thing, swam across the ocean from Africa to South America. But if the continents are squished up against each other, well, it just walked across. Yeah.
You can also line up the rocks themselves, like the Appalachian Mountains and somewhere in Europe. They have the same kind of rock.
That's exactly right. Good point. Yeah, so there are bands of continuous rock in some of these mountain ranges too. In general, there's a ton of evidence that that these continents were butted up against each other at one point in time. Again, the question is not so much whether that happened or not. The question is, how did they separate? And so the debate turns to plate tectonics and continental drift versus this expansion tectonics idea. I'm going to come back to these slides in just a second because I want to lay this on the line for you guys first. So there's these two guys in the 1950s. First was Warren Carey, and the second was this guy named Wegener. Now, Wegener, of course, was the one who proposed the theory that we've stuck with in our textbooks today. Wegener had this idea of continental drift that the one that I've presented so far, a pretty standard model you all have heard a million times, I'm sure. Carey had this other idea. He thought that a much more sensible explanation both of these people, hold on, before I get to Carey. First of all, Wegener's idea of continental drift was considered fringe science in his time. This was not a popular idea at all. In fact, I believe that he died before he even saw it take on the esteemed status that it has today. So he was a complete lunatic fringe scientist, which is really fascinating. It's actually quite tragic how this happens sometimes. There's been a number of cases where people have had completely lunatic ideas and they die before they see them come to fruition. Another famous example is, obviously Copernicus, but another one would be Semmelweis, who was the physician who started advocating for hand washing during the delivery of babies, which turned out to be a really good idea. But except all of his peers thought he was insane and they didn't want to have to wash their hands. And so they ended up ruining this guy's life, like ruining his career. And he actually died in a mental institution, which is super tragic. So this happens, honestly, sometimes. And this is why the popular idea is not always the right idea. You got to be careful jumping on bandwagons. So anyways, Carey's an interesting dude. So Carey had this alternative idea. And now, mind you, both of these gentlemen, neither one had a mechanism for how it was that the continents moved apart. So Wegener thought that the plates surfed around somehow. He didn't really know how, but they used to be together in a giant continent on one side of the Earth, and they moved away from there over time. what happened later after he was dead was that people came up with this idea that the actual convection, so that kind of roiling, bubbling surface of your teapot or whatever, was happening under the Earth's surface, and that would provide a conveyor belt to kind of scoot these continental plates around. And we'll talk about that in just a second, because there's some problems with that idea. Carey also had a pretty crazy idea, and he had no mechanism for it. And his idea was this, and this is in reverse for whatever reason, but he had this idea that if you actually just squish the Earth down, so you just make it something like 40% of its present volume, all the continents actually just fit together perfectly. And he was arguing that if you try to make them fit together in the continental drift idea, that they actually don't fit together that perfectly. They sort of fit together, but there's these huge darts, and then there's these huge open gaps where they wouldn't fit together. And he's like, look, if you just shrink the Earth, they fit perfectly together. And that was pretty much the extent of his argument. So, like I said, the world kind of wrestled with this. I actually think that Carey proposed some really bizarre, yeah, please.
Would that theory kind of feed into why the ocean is so young?
Yeah, would it? I don't know. I'm actually a pretty big fan of this idea, but with a caveat. So I'm gonna get there in a second. Like I said, neither one of these guys had really any idea how this happened. There's still a number of, like if you go to YouTube and search for expanding Earth or something like that, you're gonna come up with people who have the most insane explanations for how the world would have expanded. Most of them are like, it's accumulating stuff from the sun, or like, you know, cosmic rays or something like this, right? And I'm not really persuaded by any of those arguments. That would take, again, quadrillion years or something like that. The other problem that Carey suffered from was that I think he was pointing to chemical reactions that actually caused sort of this kind of boom thing of the Earth that caused it to expand. The problem is if you took all the chemicals on the Earth and you just added up the activation energy from all those chemicals and exploded them in a room, you would not have even a tenth of the energy that you need to actually expand something this massive. So that didn't work out. And like I said, people came up with this conveyor belt thing, and it was quite popular. So let's look at that one for a second. So this is the basic idea. You have these convection cells. They result in either the spreading of the seafloor, or at the limbs, like over here, they would result in subduction, right? You guys have probably heard of the subduction zone off the coast here. And it certainly appears that one plate is overlapping one of the other plates. That doesn't seem to be a dispute from either camp, really. So what's wrong with this picture? This is the one that we've kind of inherited. Well, the biggest problem with this idea, this mechanism, is that it doesn't seem to be happening. So people went and looked for these convection cells underneath the Earth, and they found something else instead. Let's see if this will play. So what they found actually is that there's these things called mantle plumes, which is kind of where you actually get the magma rising up for the most part. And you get these like blossoms of, let's say, more fluid magma. And they don't seem to align in any way, shape, or form with the actual margins of the Earth, which is really, really weird. So that doesn't make any sense. So they haven't been able to find these convection cells, which is a bit troubling. And so, for me, I'm still left a little puzzled by how these plates move around if we don't have these nice convection cells, and that's the only mechanism we can think of for how this would happen. So the question then becomes, how in the world would, if Carey turns out to be right about this, how in the world would it happen? How in the world would a planet balloon up, let's say? Now there's two really interesting people I talked to personally. I recommend both these guys. One of them is actually an astronaut. I think he's actually he's headed to the ISS this month or very soon. That's Don Petit. He actually did his PhD here in Oregon. He's a cool guy. I've talked to him a bunch of times. But it's interesting. He did his PhD on this really bizarre problem in the physics related to an archaeological question, which is the Quetzalcoatlus. Does anyone know what that thing is? Quetzalcoatlus.
I've only heard of Quetzalcoatl.
Quetzalcoatl, feathered serpent, right? From the Mayan religion. There's actually a bird named Quetzalcoatl too. really cool looking bird. If you ever go down to see the pyramids in Guatemala, you'll see these birds all over the place. Neither here nor there. Quetzalcoatli were dinosaurs. They weren't exactly dinosaurs, but they were bird-like, giant bird-like things. They had huge wings. So what Don Petit studied with his advisor, I can't remember his name, I feel really bad about that at the time, who was also at University of Oregon, they studied the flight characteristics of these birds, these giant birds, and they're huge. They're like the size of a 737, right? Their wingspan's enormous. Turns out they were just too big compared to the size of their wings that they could have ever sustained flight. So you have this giant bird thing. It's got huge wings. There's no way that the physics could have allowed for these things to fly. And at the time, people were like, well, they could have just been like flying squirrels, like they jump off cliffs or something like that. And they did the math on that, and they were like, no, that doesn't work either. So either of these bird things didn't fly, they just had wings because it's cool to have wings, I guess, or something else was going on. And so what else could be going on? Ideas? Yes? If the Earth was smaller. So the proposal that I am going to make to you does not consider that the actual mass of the Earth changed at all. But that's a reasonable conclusion. Yeah?
The atmosphere was thicker?
The atmosphere is thicker. So check it out. You might not realize it, but how do you float in a let's say you go swimming in the ocean? Like, what's the basic idea there? Anybody? Yeah, buoyancy. Can you explain it to me? Anybody?
You like displace water, and so you have to displace like an equal amount of water as what your object how much it weighs.
Yeah. And if you displace more of it, right? So let's say if your density is less than the water, then gravity is going to push all that water underneath you, and the result is that you rise up. So the reason that works out in the ocean is because, well, you're mostly made out of water, first of all, except, you got some other voids inside of you, and you've got air in your lungs and stuff like that, which ultimately gives you a little bit less density, right? A little more volume than the water would occupy. So water goes underneath you by gravity, pushes you up, and you float. The proposal that Don Petit was exploring and his advisor was that, you know what, you wouldn't really need that much thicker of an atmosphere to get these things to fly, actually. I think that they calculate something on the order of 3 times as thick. Now, what do they mean by thickness? They just mean density, it turns out. So one of the things that they fought against when they published this paper, this was like, 20 years ago or something. One of the things that people pushed back, they're like, oh, well, like, we know the elemental abundances back then. We know the oxygen ratios, right? Because we have these core samples. We talked about them in the climate discussion. And he's like, you know what? I'm not talking about the actual relative amounts of the different species in the air, the different elements, right? He's like, there's no actual way to look at anything in the fossil record and tell the partial pressures. Right? So you can say, well, there's 20% oxygen in the past or 18% or whatever, but you can't say if there was more air overall. You just know the ratios of the different elements in the air. So there's no way to actually know what the pressure was in the air back in the time of the dinosaurs. Yeah.
There are arguments that the reason why dinosaurs and animals in general were so big was because there was more oxygen in there.
I haven't heard that one. There might be. And there might have been more oxygen in the air. You can only have so much oxygen in the air, though, too, because what happens if you have too much oxygen? Yeah. It's oxygen is one of the most flammable substances in existence. So you don't want to light the atmosphere on fire. Also, oxygen seems to have not been here so much in the beginning, at least in the gaseous form. So it seems like it was generated over the years in sort of in some burst when plant forms appeared, plant-like algae, little unicellular planty things. But I don't know. I think we have a pretty good grip, and maybe it has increased or decreased a little bit. I'm not sure. I'd have to look into that. But I think that the argument is that it was more or less the same ratio of oxygen and nitrogen to trace gases that we have today. The question is just how much of that stuff was there overall, right? And there's no way that anyone's figured out for deducing that. And so, yeah, so Petit and his advisor make this argument that, hey, 100 million years ago, it's not entirely unreasonable that the Earth would have had a much thicker atmosphere. And guess what? That would make everything about the dinosaurs make a whole lot more sense all of a sudden. Because there's more problems related to this besides the flying birds who can possibly fly. The dinosaurs are enormous. Getting something that is the size of, a large apartment building to walk down the street without breaking its own legs is almost inconceivable, given the current situation. Arguments could be made that some of those brontosauri and stuff were lake-dwelling creatures, right? I think there can be good arguments made about that. But there appear to have been a lot of these huge, huge animals that frankly defy physics otherwise. So anyways, Petit and company argue that the atmosphere was at least 3 times thicker in the time of the dinosaurs. Now that's interesting. So the question becomes, how much thicker would the atmosphere need to be to squish the Earth down to the size required for that picture that we pulled up earlier? Let's see here. Sorry, getting out of my order. How thick does that atmosphere need to be? And the answer is it needs to be like huge, like the size of essentially something like Neptune to be able to do that. So, of course, then the question becomes, how in the world does it lose all that atmosphere? Maybe you can lose some of that. Maybe for Don Petit's idea about the dinosaurs, it loses 2/3 of its atmosphere when it gets smashed by this huge meteor that kills off the dinosaurs. That's a reasonable hypothesis. But how do you lose, hundreds upon hundreds of volumes worth of the atmosphere? I don't know that there's a really easy answer for that, especially given the time constraints that we need to be able to tell a story about the solar system, unless, of course, things take a lot longer. There's also, in the last few years, been a lot of observations of gassy and Neptune-like planets that end up too close to their sun for some reason. And what's interesting, they call them hot Neptunes, hot Jupiters. And they're getting their atmospheres cooked off. You can see the atmosphere essentially flying off like a comet tail from these things. So the natural hypothesis is, I guess the theory would be that in order to explain this small to large expansion of the Earth, you would need it to essentially elastically decompress by losing its enormous atmosphere, either through some catastrophic event like the Earth had a very different orbit at some point in time. It lived some of its life as a Neptune-like planet, and then it got too close to its star, to whatever star it was orbiting, maybe ours, I don't know, and it blasted off its atmosphere. And then what happened was that not having all this pressure, the kind of brittle crust eventually weakened and gave way to a series of expansive events. Another interesting piece of support for this is, like I mentioned, the age of the ocean floors. It's only 200 million years old. The oldest parts of the ocean floors, which constitute a huge part of the surface of the Earth. So how do we get these enormous ocean floors over 200 million years? It's a great question. Like I said, the seafloor spreading is often advanced, but you don't have those actual plumes of material coming out from there like is often required in order to make for that nice seafloor spreading hypothesis with plate tectonics work out. So continental drift and expansion tectonics. Those were the 2 big arguments. I don't know, man. It's what do you guys think? How does this sit with you? Yeah.
How they say like volcanoes explode and then the magma cools. I don't know if that's like how new landmass is made.
Yeah, for sure.
Could it be argued that something like that happened inside the Earth?
I mean, that's in some sense part of the whole story. Yeah. Yeah, that's kind of exactly right. The question, the question is, when I look back at this history, if I'm going to entertain the expansion tectonics thing, it doesn't make sense to me that it would have happened very slowly over all this time because, well, the ocean floor is only 200 million years old. So it seems like a lot of the expansion, if there was expansion, happened in a very short amount of time. Because 200 million years is nothing compared to like even the mainstream story, 4.5 billion years, that's billions of 1,000 million years. And we see the oceans expand in 200 million. So why was it so sudden that this occurred? And I think that it has to do, if I wanted to explain that, I would probably have to say that the crusts cracked open, essentially, kind of like an eggshell. And when they did, the softer material underneath was able to expand, whereas it was just under a great deal of tension prior to that. Yeah.
What if it was like kind of like a combination of the two? Because I mean, you're talking about how we are pretty sure about like subduction being an actual thing. And so what if part of it was, I mean, your ocean floor is only 200 million years old, but it's this continuous like recycling that still happens there, but is still getting like, you're still getting larger and larger. So you have less subduction than you have creation of new ocean floor. And so it would still explain a young ocean floor, but you're still expanding.
I mean, in all honesty, I think that the truth is always somewhere in between. Not always, but often somewhere in between when you have these countervailing ideas. There does appear to be these subduction places, although it's really weird. I would urge you all, if you're interested in this topic, to go check out the USGS vector maps of the motion of the crust, because they'll have these little arrows that show you where the crust is moving. It is not moving in any way that makes any sense to me whatsoever. There's these vectors pointed all over the place. There's pieces moving this way and that. They're definitely not doing this nice dance from the Pangea thing that were fed as a simple version of this. And this other guy, by the way, Marvin Herndon, he's kind of an interesting character. He's a little bit of, an outsider, but he was a very famous, actually, geochemist. He worked under, I believe, Uri Geller, who was the guy who did the initial mad scientist experiment trying to make life happen inside of a chamber back in, I think it was like the 30s or 40s. Anyways, this guy was actually quite popular for a little while. He was on the cover of Discover magazine back in the early 2000s. He had this interesting, to address your question, he had this interesting example that he provided, which is like, if you take an orange peel, just take the peel off the orange, and you try to put it on a watermelon, what happens is that, it's gonna, like you're squishing it down, it's going to wrinkle up in certain places, which would explain mountain building really nicely. And B, that some of the little pieces, as it rips, are going to slip underneath the other pieces. So he tries to explain subduction in that way. But I don't know the answer to this, to be honest with you. I'm just very dissatisfied with the Pangea continental drift thing. And as far as thinking about the metamorphic idea of planets, and there's more evidence that fits into this model than just this. But the idea that you can create something really dense, remember, we're on the most dense thing in the solar system. How the hell do you do that, right? It doesn't seem to be as simple as just a gravitational collapse situation. And so this idea that was started by Carey, sort of abandoned for a while, it might have more validity to it than it seems on its face. And so it'd be interesting to see if this makes a reappearance in the future. Any other thoughts about this? Okay. You guys can think about it. Think about it. On the list of crazy theories you heard in this class. Okay, let's talk about magnetism. This is good. So we obviously have this magnetic field. It's polarized. Yes?
Sorry, I know you just said like English stuff.
No, hit me. It's all good.
Not necessarily like radical new thought, but when I had watched the video that you were like watching, I thought it was really well done and a new way of looking at things. And so I think it does make sense and something that's really interesting to discuss.
Cool. I'm glad you think that. I mean, look, here's the thing, folks. It's like science is full of crazy ideas. It's really a matter of which one's the craziest at the end of the day, and which one's, can we get rid of some ideas? And I don't think we can get rid of that idea yet. I think it was gotten rid of prematurely. So I don't know if it's true. I don't know if any of the stuff I'm telling you guys is true. They're just ideas. They're just theories, right? They make sense. Yeah. We'll get to you then, too.
The discussion we were having with the thick atmosphere.
Yes.
I was just thinking, I can't remember if it was a moon or a planet, but we were talking about some moon or planet that had like such a thick atmosphere that it like almost stopped the seasons, or it's like it was just always hot on that. Like,
Oh, Venus. Yeah, Venus is pretty gnarly.
so.
But that's mostly because it's not rotating.
Oh, gotcha.
Yeah.
That answers the question.
But it's pretty bizarre. We'll look at Neptune and Uranus, which are a class of these, we call them ice giants, not really icy. But they have, they definitely have a ton of water on them, and they have a big rocky core that's basically the same composition as the Earth. So you got all the ingredients you need to make this pizza. It's just a matter of whether you have enough time, really, as far as I can tell. Yeah.
Yeah, I was definitely thinking about that expansion theory a lot. I did call, I don't really know that I do anything about. But.
Wait, sorry, I didn't hear that part. Say again.
I called my dad and my boyfriend. I was like, wait, no, listen, but what if the Earth expanded? He was like, but what about the Dawn plates? I was like, I'll just send you the video. I don't want to talk about it. Just send the video.
It's gonna get me. I'm gonna lose my job. Good lord.
Yeah, because it just seemed so like, of course.
Yeah.
Me personally,
Yeah.
like, really was like, of course that is what happened, rather than
Yeah.
giant block of all of the land and then it expanded.
Yeah.
But it does also make me wonder, like looking at other planets and like the universe as a whole, isn't it expanding? Like, isn't the whole universe expanding?
I'll have to deal with that next semester. It's too big.
Right.
Some would say, yeah.
So that's why I'm thinking, well, wouldn't it just be in? I know that
Like cosmological explanation for it, basically.
Right, but I don't want to. I hate to use words like this. It's trying to like debunk a lot of the like laws of science or scientific laws, but then like, wouldn't it be a law feature that everything's kind of wouldn't that make a lot of sense if the Earth expanded, if things are expanding, and that's.
I mean, I'm not going to crack open the cosmology right now. It's just too big of a monster, and I have serious problems with it, but I want to be careful about them, so I have to present the standard cosmology. So please, sign up for the class next semester. You did? Oh yeah, please do, and I promise we'll get to the bottom of that. I mean, I'll tell you this, when things cool, there's expansion when things cool. So that's worth considering too. Anyways, it's a huge topic. I don't know if it's true or not. I don't know which ones. I don't know. Nobody knows. The question is, what makes the most and the least sense to you is really what it comes down to. So let's talk about magnets though, because we've got about 15 minutes left, and I really want to make sure you guys understand magnets. Yes. Last question. I mean, one last question about it, but we can talk about it at the beginning of next class too. Yeah. I want you guys to sleep on this a little bit.
With the expanding Earth,
Yes.
if we go with that, how would you explain all the other supercontinents that we've had?
All those.
There's more.
It's really hard to get to the bottom of it. This is supposed to have happened several times. You're right. But these fossil records only go back to the last one, so I'm kind of capping my analysis at those. Yeah, I don't know. I'd have to look at that data more cleanly. I find it compelling because of the fossil record that the continents were glued together at some point. So for me, I'm just trying to explain how they came apart. But yeah, whether they came apart multiple times, I don't know. I really don't know about that.
They came apart and they came together and then they did that.
It depends. Yeah, I've had a hard time finding anybody to make that argument. If you can find a reference for that actually makes that argument in a good way, I'd be interested. But I've generally seen the argument bounded to just this most recent drift, continental drift thing. But you're right. Depending on what textbook you look at or where, there's lots of versions of how this went down. There's lots of versions of whether the Earth had a lot of water in the beginning or not. That's a really interesting piece of the puzzle too. Anyways, all right. So look, the magnets are important. They're important not only because they're the only reason we're probably alive right now, because they protected this place. They're also important because they kind of form the bedrock of our technology. And so I want to make sure that you guys have a chance to grip magnetism in general. And that's going to set us up for understanding why we have a magnetic field in the first place. And so if you go looking on the internet about how in the world magnets work, what you're going to find after you suffer through some really miserable pop sci videos, is that atoms are tiny magnets, right? And I remember the first time I was teaching a physics class in grad school at Barnard College across the street, and I had to explain magnets to these kids for the first time, and I was completely freaked out because I could not come up with an explanation other than atoms are tiny magnets, which is like the worst explanation ever, because what the heck is the magnet on the atom, right? So I want to propose to you guys not a new theory or anything, but just a way of thinking about this that makes sense to me and that's congruent with the way that we understand the atom. So I broached this subject before to you. What we're looking at here, I'm going to grab a piece of chalk. What we're looking at here is the radial distribution of the atom. So in other words, the location of the surface of the atom. This is the electron shell, right? So if you have like your center of the atom, which is like right here, which is generally called the nucleus, you have this kind of shell around the outside, right? And what's really weird about the shell, and I've brought this up when we were talking about light and gravity before too, is that it doesn't just end right here, where the shell is supposed to, well, we define the shell normally for the atom. It actually keeps going indefinitely. So you have not a large, but some small chance of detecting the electron, the outer surface of the atom, at any distance from the atom, which is really, really weird. But I think what it does safely tell us is that the outer surface of the atom at least has some sort of pieces of it that stick out really far, actually. I don't know what that structure is, but I think for the purposes of this discussion, I want you guys to think about the atom as sort of furry on the outside. It's got long hair, and the hair is standing up really far. That would give us a nice radial, this sort of exponential fall off of the surface of the atom. So when we start trying to ask what the heck magnetism is, first thing to realize is that magnetism comes from atoms. Atoms have a surface. The surface seems to have some sort of extended structure that reaches out really far, further away than the actual atom itself, at least to its neighbors, right? And the next piece of the puzzle is that the surface of the atom, the electron, appears to be some sort of motion. It literally is a motion of the atom. So that motion is generally qualified through this concept of spin. So electron spin is something you guys might come across in your chemistry classes. Now, what the heck is spin? Spin is the angular momentum of the electron. But it's not simple. It's not just like an orbit where it's flying around in one direction. What's weird about electron spin is that it has a strange symmetry, which means that any point on the surface has to travel around the outside twice, 2 revolutions, in order to get back to its same place. This has always boggled the minds of quantum physicists because they say this is just like an example of how the quantum world doesn't have to make any sense, and yada, yada, yada. So don't worry about spin. It's not really a physical thing. It's just a property. This is really dissatisfying. So one way I've found of illustrating this principle is like this. So if you have the surface of the atom, the electron, which is actually revolving, but the surface is also involuting through the center of the atom, what happens is you can have a point that has to go around twice in order to come back to its starting point. So I'm not saying this is the case. I'm saying that this is a good way to visualize exactly how spin 1/2 might work. The other nice thing about, I'm going to play that again for you guys so you can see that. I haven't figured out how to make this thing loop. Do it. DeLay. Come on. So you could have spin up or spin down depending on which way this thing's turning. The interesting thing about that is it gets us a little closer to the next piece of our puzzle with magnets, which is, okay, the atom is a tiny magnet. Great. Let's go back to that picture. It has this, this is actually not even accurate, but it has some sort of magnetic field to it. Now, what's interesting about this is that we have a couple of interesting other rules from physics that we know. If you take a wire and you drive a current through it, right? It's interesting because you get magnetic field effects that seem to circle the wire. They call this the right-hand rule in physics. You guys heard of this before? So you just point your thumb in the direction of the current, and you wrap your fingers around it, and that's the direction of the magnetic field. So we go back to our atom over here, and we say, okay, the atom has, I'm going to use a different color. It has a magnetic field that wraps around it like this. Great. And it has arbitrarily, just by definition, a electric field that goes, let's say, up the center of it so that it obeys the right-hand rule, which is nice. This is really nice because what we can say, using this visualization of spin 1/2 that I showed you guys earlier, is that as the surface of the atom is turning, it also has an inward motion towards the top. So you actually have this action at the equator, which we'll use to represent magnetic action, and it has an action that's up the atom, which we'll use to represent the current. So in other words, what I'm saying to you, and I guess what everybody would agree with, is that electricity and magnetism are two aspects of the same motion of the atom. So the atom's doing something weird, and depending on which way you look at it, if you look at its equator, that action is called magnetism. If you look at it in this direction, that action is called the electric field. So why am I showing you all of this? Well, what's really interesting is that if we make a wire like this, simple wire, and let's just imagine that we could somehow make this wire have, it's just single atoms in a column all the way down like this, right? This is a single atom wire, which is impossible, but let's go with it. The motion of those shells, if you line them all up and they're doing this kind of thing, so hard to work the mouse on this projector. Good grief. What you notice is that that surface, which I've drawn a little pink line on, is pushing. So if this one has some electrical charge, it has this spin charge to it, it's pushing this next atom, it's pushing this next atom, and the surfaces are pushing each other down the line. And so the way of thinking about it like this is that the electrical current is really just a propagation of motion of one atomic surface to the next, all the way down the line. You don't have little electron bowling balls flying off of each atom. You just have one surface pushing the next, which is completely rational and easy to understand. There's serious problems with the idea that electron bowling balls are flowing through a wire. When they try to measure the motion of these electrons, they're much, much slower than the actual action. If I close a switch, you actually, at the speed of light, will see a light bulb light up at the other end. The electrons are only said to move at some minuscule fraction of that amount. So that model doesn't really work anyways. I think this is a much better way of thinking about it. Now, also the result is if I have that spin motion going on for all these atomic shells, the result is that you have a combined field. All these guys are turning in this direction. And if you consider their extended structure, all of a sudden you have this moving extension of the atoms that's actually reaching out in all directions. You actually have that equatorial motion that is the magnetic fields going on. Now, why am I telling you this? Because the cool way that you can actually amplify this process is take that wire and actually bend it in a loop like this. We call this thing a solenoid. So I'm just taking this wire. Now I got all these, this is just a single atom wire, right? I got all these little atoms. And they're all moving with going into the board. They're all curling into the board, so they're turning into the board. The cool thing is that all along the coil, you get everybody turning into the board the same, right? So everybody's kind of working together. And what happens is you get an overall field now, like this through the coil, because everybody's turning at the same rate, because their equators are all aligned when you turn that wire on the side with these coils over and over again. So the coil is a great amplifier of the magnetic ability of a single wire as it's passing current through it. And we make use of this technologically. I think I'm not going to have time to explain how this happens in the Earth. I'll get to the beginning of next class. But last thing I want to show you guys is how this thing actually works in real life. So we make use of this all the time. This is how we generate power for our civilization, essentially, right? So what we have here, I actually made this one out of a pen and some wire, and these are just static magnets. Let me show you the process here. What I've done this is I made one of these little coils of wire like this solenoid over here. Now, obviously, each one of these wires that I've wound into this coil has way more than one atom in it, but that's okay. The same thing applies with multiple atoms, as long as their shells are aligned like they should be. Fortunately, they tend to align themselves when you drive a current through it. So there's two coils going on here. There's also static magnets. We can talk about static magnets, how the heck those work next time, because we've been talking about electromagnets so far. But the result of it is that when there's no electricity flowing through the circuit, nothing happens. These coils have no magnetism at all, right? They don't feel anything whatsoever. There might be like a little bit of attraction to the metal if it's gotten magnetized over time. But anyways, nothing happens. What happens though is when I do put current through this coil system, you get the production of a magnet all of a sudden inside this coil. And the result of it is that there's a south pole generated over here and a north pole generated over here. And when the north pole faces the north pole of another magnet, those motions are counteropposed. They push against each other like this. Ah, get away from me, right? So the extended structures of those atoms is batting each other away at that point. So all you have to do to make that magnet appear is to drive a current through it, which is going to align all those shells. And I'll give you guys a little demo here. Give it a little kick. Oh, there it goes. All right. So that magnet, it comes over. And let me just show you real quick slowly. So the magnet appears, and boom, it kicks it over because it's repelled. And then the current swaps. Now the south is facing the south over here. Boom, kicks it. And so you have this creation of a magnet for just a split second, long enough for it to give a kick so the wheel can turn over. Now this is powered, but you can imagine that in all of our energy generation systems, from nuclear to coal burning to anything else, the photovoltaic stuff with the solar cells is a bit different. But what's happening is people will run this thing in reverse. So they drive a turbine that spins this piece, and as it spins, it creates a magnet, and when it does that, as it spins, what happens is that it magnetizes the coil. These permanent magnets magnetize the coil, and they drive a little bit of a current back down the line. And then the next kick happens, and a little bit more current. And you make a battery, and you fill up the battery. You charge up the battery is a better way of putting it. And voila, you have a power system. And I'm almost out of time, but actually, just think about it wait, we're on the weekend now, right? Yeah, think about it. Have a good Halloween. Think about, are you guys voting this year? All right, spend some time. Remember, the local elections are super important, so spend some time figuring out who sucks and who doesn't. And I'll see you guys on Tuesday. We'll pick up all the loose ends.